What if I told you that deep beneath our very feet, there's a pulsing ancient heart? A heart that has been beating for billions of years, dictating rhythms that shape our entire existence. We see its breath in the swirling mists of Iceland's blue lagoon, its vibrant colors in the grand prismatic spring of Yellowstone, and its raw power in the erupting geysers of Rotorua. But these are more than just beautiful tourist spots. They are windows into the Earth's fiery soul. When we think of geothermal, hot springs and volcanoes probably come to mind. And you're not wrong, but that's just scratching the surface. Imagine the Earth as a giant engine, fueled by a core as hot as the sun's surface. This incredible heat isn't static, it's a dynamic, flowing force. It moves through the planet's mantle in slow, powerful currents of molten rock, a process called convection. This is the Earth's internal heat engine, a geological process that has been running continuously since our planet's formation. It's the force that pushes continents apart, raises mountain ranges, and creates new ocean floors. So, these ancient rhythms aren't just historical curiosities locked away in geology textbooks. They are active, living forces that are influencing our world right now, from our climate and weather patterns to our search for sustainable energy, and even our understanding of life itself. Stick with me as we journey to the center of the Earth, metaphorically speaking, to uncover these geothermal secrets and reveal what these ancient rhythms mean for us today. Let's start with the basics. The Earth is structured in layers, kind of like an onion. At the center is a solid iron-nickel core, surrounded by a liquid outer core. The immense heat from this core, left over from the planet's formation and fueled by the slow decay of radioactive elements, needs to go somewhere. It radiates outwards into the mantle, a thick layer of semi-molten rock. Think of a pot of water simmering on a stove. The water at the bottom gets hot, becomes less dense, and rises. As it reaches the surface, it cools, becomes denser, and sinks again, creating a continuous loop. This is convection, and it's happening on a planetary scale inside the Earth. These massive, slow-moving convection currents in the mantle are the driving force behind plate tectonics. The Earth's crust, the thin, solid shell we live on, is broken into large pieces called tectonic plates. These plates are constantly drifting on top of the flowing mantle, like rafts on a slow river. Where plates pull apart, magma from the mantle rises to create new crust, forming mid-ocean ridges. Where they collide, one plate can be forced under another, a process called subduction, leading to intense volcanic activity and the formation of mountain ranges like the Andes. And where they grind past each other, like along the San Andreas Fault in California, the built-up stress is released as earthquakes. So all this geological drama, volcanoes, earthquakes, mountains, is a direct expression of the Earth's inner heat. And this is where it gets really interesting. These processes aren't random. They follow deep ancient cycles, rhythms that play out over millions of years. Scientists study these cycles by looking at the geological record. They analyze rock layers, ice cores, and seafloor sediments to piece together the planet's history. For example, they've identified what are known as supercontinent cycles. Over vast stretches of time, Earth's land masses have repeatedly come together to form a single giant continent, like Pangaea, and then broken apart again. This cycle of assembly and breakup is driven by the underlying mantle convection and has a profound impact on global climate, sea levels, and the evolution of life. When a supercontinent forms, it acts like a giant blanket, trapping mantle heat beneath it. This eventually leads to rifting and the continent's breakup. The breakup changes ocean currents and weather patterns, triggering dramatic shifts in the global environment. These aren't just abstract concepts. We are living in one of these phases right now, in the aftermath of Pangaea's breakup. The Atlantic Ocean is still widening, and the Pacific is shrinking. These geothermal rhythms also have a direct link to Earth's climate history. Massive volcanic eruptions, known as large igneous provinces, have punctuated Earth's past. These are not like your typical volcanic eruptions. We're talking about colossal outpourings of lava that can cover millions of square kilometers and last for 1 million years. The gases released during these events, especially carbon dioxide, can cause rapid and extreme global warming, while the ash and aerosols can block sunlight and cause short-term cooling. Many of the planet's major mass extinction events have been linked to these massive volcanic episodes. It's a stark reminder of the immense power the Earth's interior holds over the surface environment and the life that inhabits it. By studying these past events, we can better understand the potential consequences of large-scale changes to our atmosphere today. The Earth's geothermal heart has a story to tell about climate sensitivity, and it's one we need to listen to very carefully. But it's not all about destruction and drama. The Earth's inner heat is also a source of immense potential for humanity. This brings us to geothermal energy. In places where the Earth's crust is thin or fractured, like in Iceland or along the Pacific Ring of Fire, this internal heat is much closer to the surface. We can tap into it by drilling wells to access underground reservoirs of hot water and steam. This steam can then be used to drive turbines and generate electricity, providing a clean, reliable, and renewable source of power. Unlike solar or wind, geothermal energy is available 24/7, regardless of the weather. It has a tiny physical footprint compared to other power plants, and it produces virtually no greenhouse gas emissions. Countries like Iceland already get a huge portion of their electricity and heating from geothermal sources. Imagine heating entire cities with the planet's own natural warmth. This isn't science fiction. It's a technology that is already being used and constantly being improved. Enhanced geothermal systems, for example, are a new frontier. They involve creating artificial reservoirs by fracturing hot, dry rock deep underground and pumping water through it to generate steam. This technology could potentially unlock geothermal energy almost anywhere in the world, not just in volcanically active zones. It's a key part of the puzzle for transitioning to a sustainable energy future. And the story doesn't end with energy. The unique environments created by geothermal activity might hold clues to one of the biggest questions of all. How did life on Earth begin? The deep-sea hydrothermal vents we talked about earlier are fascinating ecosystems. They exist in total darkness under immense pressure and are teeming with life. But this life doesn't rely on sunlight for energy like most life on the surface. Instead, it thrives on chemical energy from the compounds spewing out of the vents, a process called chemosynthesis. These communities are built around bacteria that can essentially eat sulfur compounds. This has led many scientists to propose the deep-sea vent hypothesis for the origin of life. They argue that these hot, chemical-rich environments could have provided the perfect cradle for the first complex organic molecules and, eventually, the first living cells to emerge on the early Earth. So when we study these modern-day geothermal systems, we might be looking at a living analog for the conditions that sparked life on our planet billions of years ago. It's a profound thought. The same internal heat that drives continents and fuels volcanoes might also be the very engine that kick-started biology. This also has huge implications for our search for life elsewhere in the universe. When we look for habitable worlds, we should maybe be looking for geologically active worlds. Moons in our own solar system, like Jupiter's Europa or Saturn's Enceladus, are thought to have liquid water oceans beneath their icy shells, kept warm by tidal forces and internal geothermal heat. It's entirely possible that hydrothermal vents exist on their ocean floors, potentially harboring life completely independent of the sun. So, from shaping our continents and climate to providing clean energy and holding clues to the origin of life, the Earth's geothermal rhythms are woven into the fabric of our world in ways we are only just beginning to fully appreciate. These are not distant geological curiosities. The slow, steady pulse of our planet's heart is a constant presence. We feel it in the trembling of the ground. We see it in the steam rising from a fissure, and we can harness its power to build a more sustainable future. By listening to these ancient rhythms, by studying the geological record and understanding the forces at play, we learn more about our planet's past, its present, and its future. We learn more about our own place within this dynamic, living system. The Earth is not just a passive rock floating in space. It is an active, breathing entity, and its ancient heart is still beating strong, shaping our world in every moment. Thank you so much for joining me on this journey into the Earth's fiery core. I hope it's given you a new appreciation for the incredible forces at work beneath your feet. If you found this fascinating, please hit that like button and subscribe to the channel for more deep dives into the wonders of our planet. Let me know in the comments what aspect of geothermal science you find most amazing. Until next time, stay curious.